All right, do these three warm-up problems here real quick. So 1 and 2, write the first 5 terms. Number 3, write the next 3 terms. Start with 1. Start with n equals 1. If it doesn't say different, you always assume n is 1.
Yeah.
So anyway, so looking at these, there's what I had. That look right? Okay, and so like on number 2 especially, I mean, just leave that as a fraction. Matter of fact, you almost look at the numerator and the denominator separately as their own sequences. Now, in your homework, you had some problems that had fractions in it, and what we actually had to do was go the opposite direction, right? It's easier if I give you the formula. Now, this formula is called an nth term formula. That's different than those recursion formulas, the ones that have the k plus 1 in them and stuff like that. That's different. We're going to talk about that here in a minute because I think there's a lot of confusion of that still. A couple people came in and talked about it, and I think there's a lot of you probably should have come in and asked about this morning. But that's the nth term formula. Means the nth term, like the first term or the 100th term or the 1000th term. The nth term just means we could find any term we wanted to by just plugging in an n, some number in for n, and that would give us that term. The recursion formulas just let us go from one term to the next, to the next, to the next. Very different scenario. So anyway, on this one, on your homework, a lot of what you had to do is you had the red you were given, and then you had to write the blue. You had to write the term, the formula, what we call the nth term formula. Okay, so if you're given one like that, just look at the 3, the 9, the 27, the 81. Don't even look at the bottom, right? Just look at the top and say, how do I get those numbers? Then look at the bottom and say, how do I get those numbers? Do it separately. Right? Do it separately. So, I mean, you could, it is one of the laws of exponents we have, is that if you have a over b to the nth power, then you can write that a to the n over b to the n. So it would be legitimate to write this as 3 halves to the nth power. That would be okay. And you could think of this as 3 halves to the first, and you could think of this as 3 halves squared, which would be 9/4, and you could think of this as 3 halves cubed, which would be 27/8. But I think why do that, right? That, to me, that makes it harder. I think it's easier to look at the top and the bottom separately, and instead of thinking of 3 halves times 3 halves times 3 halves, but it's kind of the same thing. And here you're just looking for a pattern. Goes up 5, goes up 7, goes up 9, so now it's going to go up 11, now it's going to go up 13, now it's going to go up 15, right? And we talked about that pattern too, and we'll come back to that here in a little bit. All right, so let's just review what we've talked about here. So a sequence, okay? So what do we got? A sequence is just a series of terms, a series of numbers separated by commas, and there could be an infinite number of them, and there's some sort of a pattern that generates this sequence, and the little number on the bottom is our n, or it could be k, or it could be I. We can use whatever letter we want. Usually it's n. Sometimes we saw it was k. It doesn't matter. Okay, but this is the number of the term down here. It matches with the subscript, right? Sometimes, like Charlie was saying, it starts at 0, but it wouldn't. Usually it starts at 1, but sometimes it could start at 0. Okay, so here would be a sequence right here. Right here would be a sequence. Just an example of a sequence. I've written the number of the term down below it. What would be the nth term formula for this? What would be your first thought in trying to find the nth term? This is the very beginning of your homework now. What are you looking at here? What's the pattern? What's it doing? You're adding 2. What did we say that repeatedly adding 2 should make you think of? That should make you think of multiplying by 2. If you repeatedly add 2 10 times, that's 20. 2 times 10, right? So repeatedly adding 2 should make me think of 2n, but now you need to make an adjustment because n is a 1. When n is a 1, if you put a 1 in there, 2 times 1 is 2, but we wanted -3. So what did we need to do to go from 2 to -3? We could minus 5. Now, since it's a repeated addition problem, the adjustment is always going to be an addition, or in this case, a subtraction, but we can think of, I'm going to say addition, adding -5, the same as subtracting 5. Now we just check it. Put a 1 in there. 2 minus 5 is -3. Now put a 2 in there. 4 minus 5 is -1. Now put a 3 in there. 6 minus 5 is 1, and on and on and on. And it works for every term. Okay? Now we look at this problem. What's the pattern here? Divide by 2. But I'm not going to say divide by 2. I'm going to say what? Multiply by 1/2. We're multiplying by 1/2, okay? So repeated multiplication should make you think of what? Repeatedly multiplying by 1/2 makes you think what? A power, an exponent, 1/2 raised to a power. Because if you multiply by 1/2 5 times, that's 1/2 times 1/2 times 1/2 times 1/2 times 1/2. That's 1/2 to the 5th power. Okay, when you repeatedly multiply, that's an exponent. So this is 1/2 to the nth power. But now we check that, and we put a 1 in there. 1/2 to the first power is 1/2. Well, that's not 4, so we're going to have to adjust that. Now, when you adjust repeated multiplication, what do? You would multiply by something. So 1/2 times, so when you put a 1 in for n, 1/2 times what? Or 1/2 to the first, 1/2 times what would make 4? 8. Now let's just check it. So we put a 1 in for n, we get 1/2 times 8, that's 4. Now let's put a 2 in for n, right? The little blue 2 here. Put a 2 in for n. What's 1/2 squared? 1/4. What's 1/4 times 8? 2. Now let's put a 3 in for n. 1/2 to the third is 1/8. 1/8 times 8? Is 1, and so forth and so on. Seems to be working. Put a 4 in. 1/2 to the 4th is 1/16. 1/16 times 8 is 8/16, which is 1/2. It seems to be doing it for us. Okay? So those are your 2 most important patterns. Matter of fact, we're going to go on in this chapter. We're going to give these a name. A name where you have a sequence where you repeatedly add the same thing over and over is called an arithmetic sequence. A sequence where you repeatedly multiply by the same thing every term is called a geometric sequence. And so those are the 2 probably most important sequences we have. But there are other sequences. There are other patterns that we can come up with, like this problem here, okay, is a different one. Okay, what would be the nth term formula for this one right here? Well, we don't have a way of doing this like we did the first two. If you repeatedly add, you think multiply. If you repeatedly multiply, you think exponent. Now we've just got to search and think and be creative and those kind of things, and that's where some of your brains start hurting, right? Okay, that's what you got to do. Now, you could sit and look at this a long time. You could maybe just see it right away. It depends. It happens different for different people. This will not be a big emphasis on our quiz on this stuff, okay, is coming up with these. We're going to focus more on these. But what do you, anybody notice something here? What do you got? Squared. Why is it a squared? Because it goes up. One of the things I said the other day, that third pattern I talked about, is if a sequence repeatedly is going up by an increasing odd number, that's a squaring pattern. Okay? Now you may have to do some creative manipulating to get it. Now this one's pretty easy actually. Think of the perfect squares. 4, 9, 16, 25, 36, 49. What do you notice about these numbers? They're all one bigger. They're all one bigger than perfect squares. Okay, now the problem is if you just say, well, that's n squared, that's going to be a problem, because if you start here at 1, which you have to, or 0, but we'll assume 1 if we're not told different, 1 squared is 5, or is not 5, it's 1. So how would you turn it into 5? Well, you might think you'd add 4. Well, the problem is you can't do that. You can't make that adjustment. That worked on this. That worked on one where it was repeated adding, so you just add for the adjustment. Repeated multiplication, you multiply for the adjustment. We can't do that. Just try it here now. Take 2 squared is 4. Does it work to add 4? No, you got to add 6, right? So what we want is, this is 1 more than 1 squared. 2 squared. So we don't want to do 1 squared here. We really want to do 2 squared, right? So what do we have to do to the n first before we can square it? There you go. We need to add 1. So this is actually going to be n plus 1 squared. Now let's think about that. So now when n's a 1, 1 plus 1 is 2. 2 squared is 4. Oh, but then we're 1 short. So then we would add on a 1 outside the parentheses. Now let's try the next one. Put in a 2. 2 plus 1 is 3. 3 squared is 9. And then plus 1 is 10. And so forth and so on. And then it works. Okay? So that's sometimes an adjustment. So you can see 5, 7, 9, you know, you would think that's a squaring pattern. Or maybe if you just see that all those numbers are 1 more than a square, you would think that's a squaring pattern. But it doesn't mean it's just going to be n squared. You might have to adjust the n to get the square that you want. So again, there's some creative thinking that goes on with those. And so it's good. I mean, those are good problems for you guys to think your way through. Okay, let's look at, so anyway, so that's a sequence. That's finding an nth term formula. Now let's talk about those same 2 sequences, but now let's talk about this idea of a recursive formula. Recursive formula is when you use the previous term. Okay, now in your work, let me fix these to make them look like your homework. They use k plus 1. Now I'm going to use n plus 1 just so you understand there's nothing magical about the k there. I don't know why they decided to use k on those instead of n. Okay, so what would be your recursive sequence on this one? You said you were repeatedly adding 2, right? That's what you were doing on this one. So tell me what I would write right here. A what? A sub n plus 2. Do we need to make any adjustment for that -3 and all that stuff? This recursive formula does not find a certain term for us. It finds the next term. That's all it does. Okay? So, and again, some of you, I get it if you like to plug in, but I think it would be better if you can avoid that. But if you need to, that's fine. So let's look at this. Okay, on a recursive formula, you always need to be given at least 1 term. You need to be giving a starting point, or maybe you're given the 5th term, whatever. You got to be given one of the terms. Okay, in a recursive formula. Not in an nth term formula. Nth term formula, you can find any term you want by just plugging in an n. Want the first term, put a 1 in. Want the 10th term, put a 10 in. Recursive formula just tells you how to get a term from a previous term. So you've got to have a term to start with, okay? So our first term would be -3. So if we wanted the second term, right? If we want the second term, what's n got to be? 1. And if n's a 1 there, it's got to be a 1 there. So that means this formula is saying A2 is A1 plus 2. Well, what's A1? -3 plus 2, -1. There it is. And then to get A3, we would take A2 plus 2, right? Now, what would have been another way I could have written this formula? I could have written my AN here, then what would have went right here? N minus 1. Now, if I want to find A2, that means this N is a what? Now, come on now. If I want to write A2, what's this N got to be? 2, right? If I want A2, then this N is right where the 2 is. N's got to be 2. So what's N right here? 2. What's 2 minus 1? 1. So it's still, no matter, either way I write it, this formula says A2 is A1 plus 2, because N minus 1 is the term before N. Just like N is the term before N plus 1. Okay, all this formula is saying, so I would prefer you don't even do this. I would prefer you just say this term is the term before it plus 2. And that's what a recursive formula does. They're really much easier. I know it right now, they feel more confusing. They're really much easier than nth term formulas. I mean, unless you're trying to find the 100th term, that's not a lot of fun. But as far as writing them, they're way easier than trying to figure these out. Now, I think you're getting better at that, but this is just saying, oh, you're adding 2 to every term. Oh, there you go. So what are you doing to every term here? What did we say? Multiplying by 1/2. So this is going to say to get a certain term, you do what? 1/2 times the previous term. And since this is n plus 1, the previous term is n. That's the term before n plus 1. So this formula is just saying, okay, you're going to take each term times 1/2. So to get a certain term, you take 1/2 times the previous term. That's it. Very easy to write. Recursive formulas. Okay? Not all this stuff with the power. So you got to understand the difference between an nth term formula, which finds any term we want, and a recursive formula, which finds a term from the previous term. They both have their place. Okay? They both have their place. All right, but we will do much more work with these nth term formulas than we will the recursive formulas. Okay, let's go through the homework here now. So with that as a guide for us, 47 and 48 should be pretty easy now. Okay? You're supposed to find an nth term formula. Now they didn't use the words nth term formula. They use the words write an expression for the apparent nth term, right? Write an expression for the nth term. That means an nth term formula. That's what we're talking about. Okay, so what do you notice on 47? Quickly. Adding 3. So that makes you think 3n. Makes you think 3n. And then you put a 1 in, you get 3. Whoops, well, that's no good. We didn't want 3, we wanted 2. So what or 1 and 1. What do we have to do? We're going to have to subtract 2. Now let's check it. Put a 1 in, you get 1. Put a 2 in, you get 6 minus 2 is 4. Put a 3 in, you get 9 minus 2 is 7. On and on. It looks like it's working good. What do you notice here? Adding 4. So that makes you think 4n. But you put a 1 in for n, you get 4. You didn't want 4, you wanted 3. So you're going to subtract 1. Put a 1 in, you get 3. Put a 2 in, you get 8 minus 1 is 7. Put a 3 in, you get 12 minus 1 is 11. On and on. It's working good. Okay, what do you notice on this one? It's adding 3, adding 5, adding 7. That makes us think squared. But they're what? 1 less than the perfect squares. So that's pretty easy. N squared minus 1. Put a 1 in. 1 squared minus 1 is 0. Put a 2 in. 4 minus 1 is 3. Put a 3 in. 9 minus 1 is 8. Okay, looks good. Okay, what about this one? Forget the negative for a minute. 2, 4, 6, 8. It's going up by 2. So that makes you think 2n. Put a 1 in. 2. Oh, yeah, good. Put a 2 in. 4. Put a 3 in. 6. Okay, it's working. Now, what about this negative business? That's where we said you just need to take a negative 1 to the n power. Now, It might not be n power. You might have to, it's either going to be n or n minus 1, or it could be n plus 1. N minus 1, n plus 1 work the same. In other words, think about this. Negative 1 to an odd power is what? Negative 1. What's negative 1 to an even power? Positive 1. So this will just bounce, but you just need to memorize this just bounces back and forth between a negative 1 and a positive 1. That's all that does. Okay, so now when n is 1, this would be negative 1 to the first, which is negative 1. Do we want it to be negative on that first term? So what do? Let's make it a plus or a minus 1. I don't know, we like plus better than minus, so let's make it a plus 1. Doesn't matter. Okay, so now when n is a 1, we got 1 plus 1 is 2. So now we got negative 1 to the second, which is a positive 1. That's what we want. And then when n's a 2, we'll have negative 1 to the third, which is negative 1, which is what we want. We'll have negative 1 times 4. That'll be negative 4. So all we have to do is when we're bouncing negatives back and forth is put this in and then just check whether you need it to be n or n plus 1. Whatever. It's n if you want the first one to be negative. It's n plus 1 if you want this first one to be positive. Okay? Pretty simple. So you have the same thing happening on these two. So negative 1 to the n will give us our negative. And then what? Well, now I would just look at the top. What's the top? Goes up by 1. So that's just 1 n, but we got to make an adjustment. We don't want 1 for that first one. We want 2. So plus 1, right? This is your first term, second term, third term, fourth term, fifth term. Right? Well, all those numbers is 1 more than what n is. So what about the bottom? That's 2 more than what n is. Right? It's going up by 1. So that makes the same 1n, but we got to adjust it. So it's n plus 1 over n plus 2. So again, think of the top and the bottom as just separate things. And then stick that negative 1 to the n out in front. Okay? This would be negative 1 to the n plus 1 like we talked about. The top just is 1 all the time, so that's easy. And what's the bottom? Goes up by 2's, so let's try 2n. 2 times 1, oh yeah, 2. 2 times 2, 4. 2 times 3 is, whoa. Oh, it's a good thing I checked, right? See, I did that on purpose just to show you the value of checking your answer, right? Yeah, 2, 4, it looked pretty good. We're not adding 2 every time. What are we doing? We're multiplying by 2 every time. Okay, so it's not 2n, it's 2 raised to the n. So 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, and so forth. Okay, just like that. All right. Moving on. What do you got here on top? N plus 1. What do you got on the bottom? Adding 2 every time. That gives you 2n. But you put a 1 in, you get 2, not 1. You put a 2 in, you get 4, not 3. So you're 1 too big. So you better subtract 1. Right? But you're adding 2 every time. So there it is. Okay, what's happening here? It looks like we're timesing by 2. So we already said that should be 2 to the n, right? Okay, now let's talk about this one a minute. Matter of fact, let's go back to this one. So on this one, we said 1/2 to the n, and it's repeatedly multiplying by half, so to adjust it, we're going to have to multiply by a something, and we multiplied by 8. But here's what else we could have done. I really want this to be 1/2 raised to what power would give me 4? Isn't 1/2 to the negative 2? Right? Or maybe if that's too tricky for you, let's think right to this fourth term right here. We really want that to be 1/2 to what power? 1/2 to the first power, right? But the problem is, what's n on that term? 4. So how can we get our power to be a 1 there instead of a 4? How can we get our power to be a 1? Because we want this to be 1/2 to the first. And this is 1/2 to the 0. And this is 1/2 to the second. Right? How can we get that to be a 1 instead of a 4? N minus 3. Right? Now you're right. This is 1/2 to the negative 2. This is 1/2 to the negative 1. This is 1/2 to the 0. This is 1/2 to the first. This is 1/2 squared. This would be the same thing. right? This would be the same thing, okay? And maybe you like that better than that one over there. Okay, now we do know that since we do know the rule for adding powers, this would be 1/2 to the n times 1/2 to the -3, wouldn't it? Power, right? You multiply. What do you do with the powers? Multiply basically the same way you do with the powers. Add them up, right? So that'd be n minus 3. Well, what's 1/2 to the -3? 1/2 to the -3. Flip 1/2 would be 2. 2 to the third is 8. Oh yeah, that right over there. So it's the same thing, right? It's the same thing, but maybe you like that better. Maybe you want to adjust the n, kind of like we adjusted the n on this one, where we made that n plus 1 and then squared it, okay? So we could do the same thing right here. We could say, okay, we want this is 2 to the 0, this is 2 to the first, this is 2 to the second, this is 2 to the third. Well, right here on the fourth term, we want the power to be 3. So what do we need to do with the power? We want the power to be 3, but n's a 4. So what do we got to do? We got to subtract 1. So maybe a way to do that top is just to do that. 2 to the n minus 1. Now you also could just do 2 to the n, repeatedly multiplying by 2, makes you think 2 to the n, and then make an adjustment. You say, okay, 2 to the first is 2, but I want it to be 1. So what do I need to multiply by? Multiply by 1/2. Okay, 2 to the second is 4, but then I times by 1/2, that gives me 2. 2 to the third is 8, right? This is first term, second term, third term. That's why I'm doing 2 to the third, right? 2 to the third is 8, times 1/2, that gives me 4. So you can do that, or you can do that. Either one. Okay, what about the bottom? 3 to the first, 3 to the second, 3 to the third. So what's down here? 3 to the n. And I could do that here. I could do 3 to the n like that. Okay. All right, what about this one? Well, this is easy. It's a lot nicer if you put the 1 under here. But what do we got? We got 1 on top, and we got n squared. That's pretty nice. Okay, this is a doozy right here. Okay. 2, 6, 24, 120. That's not a pattern we talked about, is it? I mean, it's multiplied by 2, and that's multiplied by 3, and that's multiplied by 4, and that's multiplied by 5. So it's now, we talked about adding on odd numbers, increasing odd numbers was a squaring thing. What is multiplying by an increasing number? Well, if you're multiplying by an increasing number, and that increasing number is always just one more, actually what you think of is factorial. Because think about it, 2 times 3 is 6, and then you times by 4, and you get something, then you times by 5 next time, right? That's it. Now it's 1 times 2 times 3 times 4 times 5. Then you times by 6, right? So that's what you would think of on this one, is factorial. Now, remember, so I'm just talking about the bottom now, 0 factorial is 1. 1 factorial, though, is also 1, right? And now we get 2 here. So this is 1 factorial. Wouldn't this be 2 factorial? 2 times 1. This would be 3 factorial. 3 times 2 times 1. And this would be 4 factorial. 4 times 3 times 2 times 1. Okay, so what's down here? It's just n factorial because we want to start with 1. Now, if it had been 2 1s at the beginning, then we'd have had something different. So 1 on top, n factorial there. Okay, what about this one? Just alternating 1s. -1 to the n plus 1. I'll give you 1, -1, -1, -1, and so forth. Okay, here we see this factorial again. Now I would make this easy on myself here. I look at the pattern on the top. 2 to the second, 2 to the third, 2 to the fourth. I'll make that 2 to the first. This should be 1, looks like, and then this would be 2 to the 0, and then this would have to be a 1 again, right? Well, look at the top. Okay, so the top's gonna be 2 to the. It's got to be n minus 1, right? That's the adjustment to make. Now you can do 2 to the n times 1/2, but basically look at those powers. They're all 1 less than the number of the term. So that'd be n minus 1. And then the bottom is factorial, except where does it seem to start? 0 factorial is 1, 1 factorial, 2 factorial. So again, that's 1 less than the number of the term. So it's going to be n minus 1 factorial. Okay, so those were tricky ones there, again, whether you could see that, or you could come up with that pattern. Okay, but once you've seen it, then it's a lot easier to tell. Okay, let's just do a couple more and then we'll jump. I just want to do this one, then we'll jump down to the last part. We'll maybe look at 62 here. How are you going to jump back and forth from 1 to 3 to 1 to 3 to 1 to 3? Well,
I know this.
Well, what are you doing let's just say this. What do you do to get to there? Add 2, or you could say times 3, right? And then you could say divide by 3, but you could also say add negative 3. And then add 3, or excuse me, add negative 2. And then add 2, add negative 2, add 2, add negative 2. Well, how do you get that sign to change? Well, you just do negative 1, right? 2, so it'd be 1 plus, a little bit of a hint are these down here. 1 plus negative 1. No, not 2. I'm sorry, 2 plus negative 1 to the n, right? Because now first term, you're going to get negative 1. So 2 plus negative 1 is 1, right? Next time, when n's a 2, you're going to get negative 1 squared, which is 1. Now you get 2 plus 1. Then you get 2 minus 1, then you get 2 plus 1, then you get 2 minus 1, then you get 2 plus 1. Okay? Yeah, just leave it that. Okay, let's look at this last one here. So 1 plus, I mean, that part's easy. And notice how they wrote it. When you look at it, you think, why would they write it that way? Why didn't they write it 1 1/2, 1 3/4, 1 7/8? They did it to help you, right? To see the pattern a little bit. So it's 1 plus. Now, what do you notice on the top here? Adding 2, then 8, Okay, well, we talked about adding odds, so let's leave that alone a little bit. Let's go to the bottom. Oh, that's easier. That's multiplying 2. Multiplying 2 every time, so what's that? 2 to the n. First term, when n's a 1, we get 2 to the first, 2 to the second, 2 to the third. What do we notice now the top numbers are? It's 1 less than the bottom number. So when you notice that, when you notice it going up by repeated even numbers, it's just like multiplying by 2, but it's just 1 less. Okay, so 2 to the n minus 1. So that's a pattern you see there. The top number is just 1 less than what the bottom number was. Okay, so get the bottom pattern and then go from there. All right, so let's talk about, a lot of you were asking about 67 through 70, so let's go to that. So we already talked about the recursive formulas. I, again, want to point out that sometimes that recursive formula can be written this way. I wrote them with n's instead of k's, just so you understand they don't have to be k's. Okay, it can be written this way or it can be written this way. It's the same thing. It just says to get this term, take the previous term, subtract 4. Okay, so let's go to 67. Starting with 67, you were supposed to do something different, right? I think it was 67, right? That it started with. You were supposed to write the first how many terms? 5 terms, and then you were supposed to write the nth term formula. So combining the two things we've been doing. Okay, well this says, so if the first term is 6, what's the next term? 8, 10, 12, 14. My hope is now you can just look at this and know, oh yeah, that's just saying to get any term, you take the previous term and add 2. To get any term, you take the previous term and add 2. So they give us a first term, we just add 2. Well, now we know what to do with that, right? What's the formula for that? You're adding 2 repeatedly. 2n, make an adjustment, 4. So when n's a 1, you get 6. When n's a 2, you get 4 plus 4. When n's a 3, you get 6 plus 4. When n's a 4, you get 8 plus 4. When n's a 5, you get 10 plus 4, 14. So there's your nth term formula. Here's your recursion formula. Here's your nth term formula. Notice the difference. Okay, this one says we start with 25, then what? 20, 15, 10, 5. We're repeatedly adding what? So that makes you think negative 5n, but make an adjustment. Negative, you put a 1 in there, you get negative 5, but you want it to be 25. So you're going to have to add 30. Ran out of room. Add 30. Put a 2 in there, you get negative 10 plus 30. Put a 3 in there, you get negative 15 plus 30. So forth. Okay? All right, first term's 81. Then what? Supposed to multiply by 1/3. Take the previous term, multiply by 1/3. Next one? 9, 3, 1. Repeatedly multiplying by what? Makes you think a power of 1/3, but we're going to make an adjustment. Let's make an adjustment on our n instead of multiply by something. So we want this to be 1/3. Well, what do we want this to be right here? We want this to be 1/3 to the 0. This would be 1/3 to the, no, -1, right? Because you flip it then, and then that make 3. 1/3 to the -2, 1/3 to the -3, 1/3 to the -4. We want this one to be 1/3 to the -4. Right? Right here. This is 1/3 to the -4. So what are we going to do with our n? N minus 5. Because n's a 1 on the first term. So 1 minus 5 will give us a power -4 where we want it right there. Okay? All right, last one. 14. A of 28. 56. 112. 224. We take the previous term and multiply by -2. Okay? So what's our nth term formula? Well, to get the -1, we know what to do there. We want the first one to be positive, so we'll do that. And then what? We're repeatedly multiplying by... No. Repeatedly multiplying by... Well, we took care of the negative already, right? With the power. Now, we could have done, you're right, we could have just done -2. That's true. Since we're doing a power anyway, we could have done this, right? We could have done -2, okay? But let's just stick with this up here. Let's just say we're doing 2, okay? 2 to the what? Now, the difference is these aren't really nice numbers like we have there. So we're multiplying by 2, multiplying by 2, multiplying by 2. So let's make that an adjustment. So let's go... What do we want this to be? Let's say this is 2 to the 0 times, that's the easiest way to do this, 2 to the 0. No, the easiest way to make that 2 to the first. See, when they're nice, perfect, like cubes or 1/3, then it's easy to do what we did here. But this is 2 to the first times 7. This would be 2 to the second times 7. This would be 2 to the third times 7. See our adjustment? So this is 2 times 7, 4 times 7, 8 times 7. So it's easiest since we're multiplying by 2. We want 2 raised to a power. So let's make it 2 to the n and then times our 7. Okay? So 2 to the first. So it's easiest if I could start n at a 1. I didn't have a choice here, right? I mean, I could have made my adjustment, multiplied by 7. Okay? So we could do it either way. All right? So there would be a good way to write that one right there. Okay? All right. So let's put a few things in our notes here before we go to lunch, and then that way, the more we get done here, the more work time we can have after. All right. So what's the next thing we can do with a sequence? Okay, well, so when we write a sequence, it's just a series of numbers separated by commas. Okay, well, the most useful thing we do in mathematics with a sequence is we want to add the terms together. Now, there's a real important calculus reason for this, but then also there are some other examples too that are not calculus related. And so we use the Greek letter sigma. That's that kind of looks like an E, I guess you might say. Okay. But the Greek letter sigma to represent a sum. So we call that summation notation or sigma notation. Just think S for sum. When you think of sigma, think sum. Okay? And we've got several different things we put in that notation. Okay? At the bottom, now usually we use I. And you say, well, why? We were using N and K and stuff before. Well, N is the number of the term, so we want that to be up on the top. So we use something else, and it's called the index, so therefore a lot of times we use the letter I. For whatever reason, in sigma notation, it seems like I, J, and K are kind of the most commonly used index variables down there. Okay? Yes?
That has nothing to do with the imaginary I.
No, it has nothing to do with the imaginary number I. Right. Okay? Yeah. Nope, not at all. So, the way you read this is you say the sigma of A sub I with I going from 1 to n. Okay, so the bottom, now, the I doesn't have to start at 1. Most of the time we do, okay, and just like with the sequence, it starts at typically at 1, okay? But that doesn't necessarily, if we started this at 3, when we put our 3 in, whatever we get would be our first term, okay? So it doesn't necessarily correlate to the number of the term, okay? But anyway, whatever, this is your lower limit of summation or your starting point, and this is your ending point. You always go up by ones, and you never go backwards, right? So whatever it starts at, down on the bottom, it goes to whatever number's up on top, and it goes by ones in an increasing fashion, okay? This could even be negative to start with here, okay? All right, and so what you do is you plug in, what you do is you take a 1 and you plug it in for I. Now what we'll usually have here is some formula, okay, for I. Well, what kind of formula would it be? It'll be the nth term formula. Now I guess it would technically be the ith term formula, because it will have i's in it, okay? But you'll plug in a 1 for I, and that's your first term. You'll plug in a 2 for I, that's your second term. Plug the 3 in for I, that's your third term, and you keep going until you get to n. And you plug that in, and then that'd be our nth term, okay, or last term, whatever. Okay, so that is summation notation. Okay, so let's do a couple of quick examples. So let's say you had this one here. Okay, so that 3i in there, that's your formula. That's your nth term formula. Like I said, ith term formula. Okay. And so what are you going to do when you see this? A lot of times we'll say expand. Now, a lot of times the directions will just say find the sum, but it may say expand and find the sum. I think if it says find the sum, you should expand it anyway, and then find the sum. So what's that mean? It means you put a 1 in for I, so that's 3, plus, then you put a 2 in for I, and that is 6, plus 9, put a 3 in for I, plus 4 in for I is 12, plus 5 in for I is 15. There's the sum expanded out, and now add those up. 9, 18, 30, 45. So the answer to this is 45. A sigma represents a sum. Okay, let's do this one. Oh, now I can see I screwed that up already. This shouldn't happen. If that's a K there, this should have been a K down here. I'm just showing you it might not have an I. It might be some other one. Okay, now notice it starts at 3. That's fine. Doesn't matter. That's our starting point. So we put a 3 in for K. What do we get? 10. Plus, notice I'm not putting commas, right? Sigma stands for sum. So we're putting plus signs in between. K is then a 4. What do you get? 17. Then K is a 5. 26. Then K's a 6, you get 37. And then you add those up.
When you go 6.
90. Oh, did I do something wrong?
When you go 6.
No. K's a 3. K's a 3. Then it's a 4. Then it's a 5. Then it's a 6. Once K is done being a 6. Okay, great question. This 6 does not mean to do it 6 times. This means that's your last K value. Now, I suppose we could put K equals 6 up here, but it's just understood that's what it is. So K's a 3, then a 4, then a 5, then a 6, and you stop. So there'd just be 4 terms. I think that I added that up right, didn't I? Adds up to 9. Okay, so note it. We'll do that when we get back. Okay, and I'll talk about that in a minute. All right, so, oh, we could write this one. Okay, so last one. I thought I was going on to something else. I forgot I had this example. So sometimes it starts at a 0. So this one starts at a 0. So 1 over 0 factorial. Now here it might be worth actually writing it out. 1 over 1 factorial. You know, I didn't write it out quite like this last time. I just kind of did it in my head. But maybe on one like this, it might be better to go ahead and write it out. Okay, it's up to you. But we go, so how many terms is there going to end up being here? there will end up being 9 of them, won't there? From 0 to 8. You're going to actually end up with 9 terms. Okay? All right. We'll finish that one when we get back. When you see sigma, you think sum, sigma, sum, and you just generate the terms. This in here is basically an nth term formula, so you put in the only difference is it's an nth term formula, but when we start at, even though we start at 0 here and we put a 0 in, this is the first term of this sum, even though it's a 0 we're putting in, right? So from that standpoint, I guess you would say it's a little different than an nth term formula. You know, because nth term means find the first term, you put in a 1 for n. Find the second term, you put a 2 in for n. But that's what this is a formula that will generate the terms of this sum. Okay? So anyway, keep going here. And 6 factorial. And this is where a calculator for sure would come in. You know, and this is going to be, at some point you'll have to just get a decimal. Maybe on a problem like this, you would just say, you would just say, it might just say expand the sum. And then you can just stop right here. I'm not sure if there is, maybe under the math.
PRB.
Under PRB?
Yeah, PRB, and then it's over to the right too.
Okay, there you go. It depends on your calculator. Some calculators, it should be there on all the different calculators, but,
Well, you'd have to do
okay, so as we get closer but yeah, I mean, you should be able to go ahead and do that, right? I mean, but that part's just, of course, see, that's where I got in trouble last time, right? Just kind of like quadratic form, and I said, you guys can do quadratic form. You could do it there, so maybe we should practice typing into our calculators. All right, a couple more things for our notes then. So a couple of basic properties of sigma notation, a couple of basic properties. Now these come into play when we want to simplify a sigma, especially if it's one where we're adding up 100 terms, you know, something where we actually would not want to just sit there and literally add up 100 terms. There are some shortcuts and there are some things we can do, okay, with sigma notation. So for example, if you have a sigma of a constant, so the example I have over there is if I have sigma and inside the sigma is a 3. Well, there's nowhere to plug your 1 for your I. There's no I in there, right? So when I is a 1, this is 3. When I is a 2, it's also 3. When I is a 3, it's 3. When I is a 4, it's 3. And when I is a 5, it's 3. So it's just 3 plus 3 plus 3. So that it's just a constant sequence. Just 3 plus, well, clearly that's just 3 times 5. Okay, now notice both of these formulas on this page start with I as a 1. They only work if I is a 1 at the start. Otherwise, they don't work. So basically, all you have to do is take your constant times that top number. Because as long as I starts at 1, that top number is how many terms there'll be. Now, we were talking about that before, where we went from 3 to 6. There were only 4 terms. We went 3, then 4, then 5, then 6. We only had 4 terms. So the top number isn't always the number of terms that there'll be. Only when I starts at 1 down here, then that top number is the number of terms. Okay, so this formula works here like so. Okay, if you have a constant, then times a formula. Like, for example, on the example, or the example we had a couple of pages back, where we had a 3i here, we could have pulled this 3 out in front and written that as 3 sigma I equals 1 to 5, and then this would have been 3 times, and then I is a 1 plus a 2 plus a 3 plus a 4 plus a 5, right? We put a 1 in for I, 2 in for I, 3 in for I, 4 in for I, 5 in for I. And then this is 6, 10, 15. This is 3 times 15, which would also be 45, right? So you have a constant multiplied inside the sigma. You could just pull that constant out in front, right, if that simplifies things for you, okay? That's just, and there are some things, again, there's some calculus things, and there are some things we may run into a little later where that can be an advantage. And then one last one is if you have some things added together, if you have some terms added together inside of here, you could split that apart. So if there's a plus or a minus, so if you have different terms, now terms, different use of the word term here, different terms in your formula, then you can split it apart. For example, if I had n squared plus 2n as my formula in there, I could split that into two separate sigmas, n squared and 2n, and then on the 2n sigma, I could pull that 2 out in front, like we were just talking about. Okay? And then I went ahead and worked those out. I don't know how important it is to put the stuff in red there, but I'll give you a chance to copy down if you want to. But that's just an example of what how these formulas can work. But I get it if you're looking at it and say, well, why would you want to do that? It looks like more work, right? I mean, the stuff on the right over here looks like more work than what this would be. Where these would come into play is if this said I equals 1 to 100, okay? Because there are certain sigmas that once we simplify them down like this, we've got little formulas we can use to find those sums. So if we had 100 terms or 1,000 terms, by doing this actually does make life easier. It makes the calculation simple. Okay? But for right now, I just want you to see that it does work. Right? That you do get the same answer either way. Okay? All right. So, last thing. When you take a sequence and add up the terms, that is called a series. A series. So, you look at these two lines that I've written up here, what's the difference? A sequence has commas in between the terms. A series has plus signs in between the terms. So when we do a sigma notation, that is describing a series. Okay? And again, that top line I added up there, basically a series is just summing a sequence. Okay? So finding the nth term of a series is the same as finding the nth term of a sequence. Right? The only difference is what's in between them. Sequence, you have commas in between the terms. Series, we put plus signs in between because we're wanting to add them up. Okay? Sequence versus series. All right. So, we have two types of series. We have a finite series, right? So there's a fixed number of terms. Now that's also called the nth partial sum. So, it sounds like a big fancy thing, but if I ask you for if I give you some sequence and ask for the fifth partial sum, okay, so sum now means we're going to add up the terms, right? So it becomes a series. And if I want the fifth partial sum, that means you add up the first 5 terms. That's what that means. Okay? So the fifth partial sum describes a finite series. You are going to add up the first 5 terms. Or the 8th partial sum is adding up the first 8 terms. And an infinite series, then, is just one, obviously, that goes on forever. And we put an infinity symbol up on top of the sigma to denote that. Okay? Now, you might be given the problem with an infinity symbol up here, and then they say, find the fifth partial sum. So that's just saying, okay, they're describing an infinite series that goes on forever, but they want you to find the sum of the first 5 terms. Okay? Now, what we'll get into later is we will actually add up infinite series. That seems strange. How could you have an infinite number of things being added together and it actually comes out to an answer? Because if you're going to keep adding forever and ever, you think you just keep getting bigger and bigger and bigger. Okay, and we're going to talk about how that actually can happen. But sometimes it can't. Sometimes the answer is there is no answer. It just keeps going and going and going, getting bigger and bigger. We say the series diverges. Okay, but we'll get into that later. Okay, so finite series or the nth partial sum, and then we have infinite series, just goes forever and ever. Okay, so very quickly here, so let's say we have this infinite series up here, this summation notation, find the third partial sum. Well, here I said we were going to find out later. Well, yeah, now is later. I forgot I was doing this infinite sum here on this example. Okay, but first let's find the third partial sum. Right? Something like that. 3/10 plus 3 100s plus 3 1,000s equals what? 333 thousandths, which is as a decimal. Just 0.333, right? 0.333. But yeah, think of this. This is 0.3. This is kind of cool, actually. Plus 0.03 plus 0.003, right? 0.333. Okay, now let's find the infinite sum. Well, what's that mean? Well, that means we would do the same thing. We would just start writing out. Typically what you want to do is start writing out the terms. What is going to happen when you do that for infinity? That's going to equal 0.3 repeating, which equals isn't that right? Now, this gets into the idea that we use a lot in calculus called a limit. But think about what you're doing. So we talk about having a sum where we're going to keep adding something to it all the time. You just forever. You're going to keep adding to it. So you think the amount keeps getting bigger and bigger and bigger. So just think. So in my hand, I take 0.3. Then I add 0.03. Then I add 0.003 and 0.003. What's happening to the amount I'm adding in? It's getting smaller. The amount I'm adding in is getting smaller and smaller and smaller. The next piece that I add in is really, really small. At some point, the part that I'm adding on is so infinitesimally small that the amount is not getting that much bigger, but it is getting bigger. But the key is there's a number it will never go past, right? In other words, so when we talk about if you're adding an amount in and it keeps growing and growing and growing forever, it means it will never stop anywhere. There's no ceiling. It would go forever. What we're saying here is there's a ceiling. 1/3. It's going to be 0.33333 repeating. It can never be 0.33334, right? It never can. It's going to be 0.3 repeating. My high school teacher used to give us this example when he talked about this idea. If when the bell rings, I said, okay, when the bell rings, you can stand up, get your books and everything, and you can go halfway to the door. And then when you get there, you can go half of what's left. And then you can go half of what's left. And then you can go half of what's left, right? What's going to happen? You never get there. So how far will you travel? Or what's the limit? What's the most that you could travel? That if you could actually get there from infinity, it'd be wherever you started to the door. That would be the sum of whatever you want to go halfway, however many centimeters that is, right? And then half of that, how many centimeters, half of that, how many centimeters, and you keep going and going and going. The sum would be the distance from here to the door. Now, technically, you'd say you could never get there, right? Because there'd always be a little bit left. There'd always be a little bit left. But that would be the ending point. So whatever distance from here to here, we would say that is the sum. That is the infinite sum. We're going to talk more about that as we go along. Okay? So, it is possible to add up an infinite number of things and actually get there. and actually have a number, have a sum. Okay, there's your homework assignments. Yes, I did add a couple of my Excels that have to do with sigma notation. Okay.
That's her favorite checking pen.
At the same time, yes. Did you say basket? Gasoline.
I'm like, wait. The right actual life.
No. We got a tree on fire while I'm climbing. Still fall down. This would be an extreme sport. You climb a tree, set it on fire.